In this work, we present PnuGrip, an active, two-phase gripper design for dexterous manipulation. Dexterous manipulation involves moving an object in hand, usually through contact interactions. Planning and controlling these interactions often boils down to planning contact locations and modes, for example, sliding, sticking, rolling, and pivoting, and maintaining them through control schemes. Enforcing a sequence of planned motions can be challenging under model uncertainty and with limited sensing. Task-driven hardware design, however, can simplify both planning and execution of dexterous manipulations. We propose designing a gripper that can mechanically mediate dexterous manipulation through the use of task-specific mechanical solutions. Said gripper should enable three main features: active mode transitions to allow full control of the phases of reorientation of a grasped object independent of the grasping force, a thin profile which allows the finger to access and precisely place objects in clutter, and high bandwidth control, made possible by fast transitions between the object reorientation phases and a high-resolution encoder for sensing the rotation of the grasped object. The ability to seamlessly handle and reorient objects is particularly useful for electronics assembly and medical lab automation, where objects need to be picked up and placed in tight arrangements. Typical objects in these applications are small and lightweight. Consequently, we assume the mass and length of a typical object to be manipulated are approximately 50 grams and 10 centimeters respectively. Under this estimate, with a 4 times factor of safety, the maximum frictional torque required for manipulation is 0.1 Newton meters. Based on our observations of grippers commonly used in industrial pick-and-place applications, we aim to have a fingertip with a diameter of about 2 centimeters. We also try to minimize the thickness of the finger to allow for grasping in clutter. Finally, we want to include the ability to measure the rotation of the fingertips for feedback and control applications. We considered two possible configurations for our two-phase finger, a disc brake and a shaft brake. As per our design requirements, the finger needs to support a torque of 0.1 Newton meters in the brake phase. Assuming a uniform pressure distribution, the brake torque is computed as the product of the coefficient of friction between the brake and the fingertip, the braking pressure, the contact area, and the distance between the centers of rotation and pressure. We derive the resultant brake torque equations for each configuration to be as follows. We find that the ratio of the disc brake torque to the shaft brake torque is proportional to the effective radius r over L, the length of the shaft. We assume that r is greater than L as our design objective is to minimize the thickness of the gripper. In our implementation, L is approximately equal to R1 and R2 is approximately equal to 4R1. Consequently, the torque generated by the disc brake is approximately 10 times larger than the torque generated by the shaft brake for the same applied pressure. As such, we choose the disc brake design for our application. We now investigate different disc braking mechanisms. In particular, we discuss rigid electrostatic, compliant electrostatic, and pneumatic brakes. An electrostatic brake consists of a dielectric material that is attached to the finger body and barely touches the fingertip. In the brake phase, the finger body is charged to a positive voltage and the fingertip is grounded. It is assumed that both the finger body and the fingertip are made from conductive materials. A pneumatic brake consists of an inflatable bladder that is attached to the finger body. In the brake phase, the bladder inflates with the gas, typically air. We evaluate each mechanism based on its torque generation capability and note that the analysis presented is simplified and neglects implementation-specific details to allow a fair comparison between the braking mechanisms. We derive the resultant brake torque equations for each configuration, where P is representative of the electrostatic pressure and pneumatic pressure respectively, and pressure is assumed to be uniformly distributed. We evaluate the three mechanisms in the following graph. The geometric parameters have been set to describe the maximum theoretical contact area. As in our previous work, we assume the dielectric for the rigid electrostatic brake is a 12.5 micrometer thick polyamide sheet, as it has a high electrical breakdown voltage. Additionally, the nominal parameters of the compliant electrostatic brake configuration have been chosen to maximize the frictional force. We find that the desired torque is achieved at 960 volts using a rigid electrostatic brake, 410 volts using a compliant electrostatic brake, and 13 psi using a pneumatic brake. We select a pneumatic configuration since the 13 psi pressure source is readily available, while both electrostatic configurations require exceedingly high voltages and consequently careful installation. Based on these considerations, we use a pneumatic brake applied at the fingertip. An exploded view of our design is shown here. Our two-phase finger is comprised of the fingertip, encoder magnet, rubber diaphragm, ball bearing, finger body, encoder, cover plate, and several screws. The fingertip, finger body, and cover plate are custom machined out of T6 6061 aluminum for precision and leak prevention. This section view shows that the body of the finger accommodates a 2 mm internal pneumatic routing line, as well as a housing for a high-resolution rotary encoder assembly. The encoder magnet is placed within the axle of the fingertip, and the fingertip is mounted in the finger body with a precision flanged ball bearing. After prototyping our finger design, we move on to the characterization and validation of the proposed design. We perform experiments to characterize the following parameters: the brake torque of the fingertip as a function of pressure, the bandwidth of the control of the pressurization of the fingertip, and finally, the frictional resistance to the rotation of the fingertip as a function of grasp force. We measured the frictional torque in the brake phase to validate the linear model described previously. Since the model only has one parameter, we measure brake torque for 4 supplied pressure values. For each pressure, the finger was loaded with a weight at 5 equally spaced distances. The gauge was then held against the positioning fixture to set the initial angle, and the diaphragm was inflated, braking the fingertip. We then released the gauge and used the encoder data to record its final angle. The same experimental setup was used for all characterization experiments. The trials for which the gauge's rotation was less than 5 degrees were considered successful. This threshold was set to accommodate the small change in angle due to the small shear deformations in the diaphragm that occurred at lower brake pressures. The results are plotted in the following graph. The trials where the two-phase gripper was able to hold the applied torque are shown in green, and the trials where the gripper failed are shown in red. The white line is the best linear, zero y-intercept approximation to the boundary between the two regions. Since we are grasping with two fingers, the slope of this line should be 1.5 Newton-centimeters per psi, based on previous calculation. As observed in the figure, experimentally it is 0.17 Newton-centimeters per psi, approximately 9 times smaller. This could be due to differences between the predicted and true coefficients of friction, contact area, and brake pressure. For example, the contact area between the diaphragm and the fingertip is likely much less than the maximum available area used for the calculations. If we assume the cross-section of the inflated diaphragm is a toroid, then the predicted contact area based on the geometry of the physical finger is about 3 times lesser. A similar procedure to that previously described was used to characterize the time required for deflating the diaphragm, or void time, as a function of the supplied pressure. For these experiments, the same 4 pressure values were used with no additional weight on the torque gauge. We conducted 3 trials for each supplied pressure. The void time was measured as the time between when the brake was released by digital trigger and when the encoder measured that the gauge had rotated by 45 degrees. The 45-degree angle was selected as a conservative estimate that the diaphragm had completely deflated. We observed that the void time is almost constant for different brake pressures, and is approximately 0.2 seconds as seen in the figure. Given that the diaphragm can be inflated almost instantaneously, we can toggle between the free and brake phases at about 5 Hz. Finally, we evaluate the rotational resistance in the free phase as a function of grasp force. For these experiments, 4 grasp force values were chosen in increments of 5 newtons from 5 to 20 newtons. No additional weights were added to the gauge to test for the minimum loading case. We visually observed that in the free phase, the gauge rotates freely in the grasp, irrespective of the grasping force. We highlight the utility of our active two-phase gripper in a number of manually scripted demonstrations. The first is a simple lab automation task. The robot picks up a glass test tube off a table in the brake phase. It then transitions to the free phase. As a result, the test tube rotates to align with the direction of gravity. Finally, the robot places the test tube in a rack. Our fingers enable this task as they can grasp the test tube with low force to prevent damage and then exert the brake force required to hold the test tube at the desired angle. The low rotational friction in the free phase enables pivoting of this fairly light object, and the thin profile of the fingers allows for placement of a test tube between two tightly arranged tubes. We also conduct similar pick-pivot-place experiments with a heavier prismatic object and with a cylindrical object in a peg-and-hole setting. These experiments demonstrate that we can grasp, hold, and rotate objects with different shapes and weights with no tuning of the gripper needed in between. In summary, we present the design of a novel two-phase finger with an active pneumatic brake. We analyze several brake configurations and mechanisms and select a pneumatic disc brake since it both satisfies our design requirements and relies on a readily available power source. Our gripper has several advantages over previous designs. The most important is the ability to transition between the free and brake phases independent of the grasping force. We experimentally evaluate the performance of our gripper and note that the void time remains constant across different supplied pressures, which provides quick and repeatable actuation at a frequency of 5 Hz. Other advantages include a compact and simple design to enable grasping and clutter, and an encoder to estimate the rotation of the grasped object for feedback and control. Thank you for watching. Please contact us if you would like more information or have any questions.